Hi, hello, namaste, and we begin with the Parseval's theorem. So, to understand Parseval's theorem, we need to understand it intuitively. What does it even mean? And then we will move further with mathematical equations after this, or the maths behind what exactly Parseval's theorem stands for. But let's just understand the intuition. So, let's say we have this particle, a quantum particle, which has 5 units. The 5 unit here represents its energy. The Parseval's theorem means, it basically means is that whether we find its position, where is this quantum particle located, where is this quantum particle located, or how fast is it moving, the energy remains fixed. In this context, it is 5 units. Now we move to the definition and mathematical understanding. So Parseval's theorem, total energy contained in a wave function is same whether we calculate it in position space or momentum space. It basically remains same. What remains same? The total energy contained. In the previous example, we took the 5 units example. That means the 5 unit energy remains contained in a wave function, or is same whether we calculate it in position space or momentum space. Now mathematically, using Fourier transform, we come to this conclusion. The first conclusion that we come across is that the function psi of x's Fourier transform is phi of k, and the inverse of this equation's inverse is this phi of k, and its Fourier transform is phi x. So let's say that we are normalizing this equation. We are normalizing exactly this equation, this one, psi of x. We put this here and we get 1. Okay, now we put this here and we get 1. So we get 1 in both ways. The one which comes here is, it came after normalization of this equation and this equation, not simultaneously but individually, but the equations results are same. That therefore we mention that this is equals to this is equals to 1. Okay, now this equals to 1. What does it even mean? It means, now as per the definition, that the total energy contained in wave function is same. This basically means that the energy remains same whether we find this or this. And also note that if someone is confused with that question, we are not measuring position or momentum simultaneously. We cannot, because of the restrictions as well as the Heisenberg's uncertainty. We cannot measure both simultaneously. So we measure this or we measure this, and we get this as a result, that the energy remains same. Now we move further with the derivation. We took different notations here for the simplification because it will be better for us to understand it. So it just means the same what we did here. So capital f of k is basically the function, and its Fourier transform is small f of x, and the small f of x is the wave function, and its Fourier transform is capital F of k. It is just for the understanding and for the betterment of notations. I just write it to show that minus infinity to infinity f of x square dx is equals to minus infinity to infinity capital F of k x square dk. Now we begin with the proof officially. Proof: minus infinity to infinity f of x square dx is equals to minus infinity to infinity f of x and f star x dx. See, so this becomes this, and you are aware about this notation very well. Now we basically substitute. What do we substitute? We substitute f of x and f star x, the conjugate of this. Now what exactly is our f of x? This is our f of x. We write this and its conjugate. So I'll just show it to you what exactly I'm talking about. So our f of x is going to be 1 upon root pi minus infinity to infinity f of k e raised to I k x dk, and f star x, that is its conjugate, will not differ at all apart from the negative notation, and we also put dash to indicate that this dk is different to this dk. So I'll show you how it is. 1 upon this remains same because this is constant, and then f star, I'm really bad with putting stars, sorry about that. This is k dash, as I mentioned, minus I k dash x, and then dk dash, right? So this is our conjugate. Now this is our conjugate. Now we begin with this further solution of basically substituting this whole thing here. Now we start due to infinity. So minus infinity to infinity f of x and f of star x dx, which basically becomes minus infinity to infinity 1 upon root 2 pi. We just basically write it as it is. Now I've kept it in depth for your understanding so that you don't miss any point. And then the conjugate. Oh, I'm lacking space here. Minus infinity to infinity. I'm just writing this over here, okay? So this is k dash e raised to minus I k dash k, x, and then dk dash. And then the main part, which I should have given some space, dx. This whole equation is integrating with respect to dx, right? Now further we take out constants or whatever remains common. So root pi remains common. This root becomes square, so this becomes, this multiplies with each other, and this becomes 2 pi, not square, my bad. This multiplies with each other, and this becomes this minus infinity to infinity, and again minus infinity to infinity, and then f of k, f star, k dash, right? And this thing, we took this out, we took this out, we took this out, we took this out here. Now we left with this and this. So and of course the notations, the dx and dk dash. So minus infinity to infinity e raised to, of course, this minus this, this is I, this is k minus k dash. That's why I told you to put dash for the simplification, dk, and then this is dk dash. This is direct delta notation, and this basically becomes minus infinity to infinity. I'll just show you too. I'll write it exactly like here, just for your understanding of what exactly I mean. Dx is going to be 2 pi, and then this del k minus k dash, minus infinity to infinity f of x square dx is going to be 1 upon 2 pi minus infinity to infinity minus infinity to infinity again f of k f star of k dash 2 pi del k minus k dash dk dash. As we can take this constant out, this gets cancelled with this. So what are we left with? We are left with this becomes f of k star k dash del k minus k dash dk dash, which further becomes minus infinity to infinity f of k f of k dash dk. We can use this property. I'll mention it. This is basically if there is an integral and there is this, which we just now had, something like this part and this part, k minus k dash dk dash, this basically becomes g of k, which becomes very handy for this solution of Parseval's theorem. So we get this, and then
so our equation becomes minus infinity to infinity f of k square dk, and we hence prove it, right? Now we have proved this. So as you see, in that case, thank you so much for watching.